Hello and welcome to today's CyVerse Focus Forum. Today's webinar is on BioContainers presented by Amanda Cooksey. I'm Tina Lee, CyVerse's User Engagement Officer. I'll be turning over this webinar to Amanda shortly, but first some housekeeping. Today's presentation is roughly 30 minutes with Q&A time at the end. So please be sure to open the Zoom chat window and type any questions you have there for Amanda. We'll cover those at the end. Materials from today's webinar, like the presentation slides and a YouTube video, will be posted on a wiki page that you can revisit at any time. And later today, I'll email you the links to that wiki page and to a brief survey to get your feedback on how we do and any improvements or suggestions you have for other webinar topics. Also, I wanted to let you know about two trainings that CyVerse is offering. Container Camp and Foundational Open Science Skills Camp. We're calling that FOSS. Container Camp is a 3-day intensive in March on everything about containers, including biocontainers. So you may be interested in that. And FOSS is a 2-week camp in June intended to give new PIs and early career researchers a solid foundation in free open source computational resources, as well as open science skills and best practices to implement their projects more effectively. I'll put the link in the chat window to our website learning page where you can find out more information about these trainings and to register. So without further ado, I'd like to introduce today's presenter, Amanda Cooksey, who's a science analyst at CyVerse.
Hi everyone, welcome to the BioContainers Bonanza on this wonderful snowy Tucson day. So we're all very excited around here. This is our third in the series of webinars we've been putting on about container technology. And if you haven't seen the first two, I hope I've done a good enough job that you won't be lost without them today. But they're definitely worth a watch. So when you get a chance, have a look at those. They're on YouTube and the slides are available on our wiki. So who am I? I am definitely a biologist. I started as a cell biologist, but it's been years since I've actually done that. Like lots and lots of people, I've spent the last 10 years or so doing genomics and transcriptomics work, and because of that, I've become much more involved in computing than I ever was before. And so I've been working with containers for about 2 years now, which is when I started at CyVerse. And I mostly use biocontainers to integrate tools into the CyVerse discovery environment, which is something I'm going to show you how to do later on today. So what we're going to cover is just a basic review of containers, mostly terminology because there's a lot of jargon involved, and particularly if you're a biologist, it's jargon you're not necessarily familiar with. I want to give you a little background of the BioConda project, which has done a fabulous job in providing packages for biocontainerization. And the biocontainers themselves, how you can get them, where you can get them, what you can do with them. And then last but not least, I'll show you how to integrate a biocontainer as a tool in the CyVerse discovery environment. So some basic benefits of containers are that they're platform independent. You can run it on your laptop, you can run it on an HPC, you can run it on a virtual machine, you can run it on any operating system. And so of course this makes them highly portable because you build the image once and then you can run it anywhere you need to. Which contributes to reproducibility because once the image is built, it always contains the same version of your tool and all of its dependencies. You don't have to worry about updates. You don't have to worry about when your lab mate runs it, if it's the same because their computer is different. So you always know you're getting the same analysis. And though it's a little beyond the scope of our talk today, containers are also scalable. As I mentioned before, you can run them on larger machines or you can run many, many instances to get your analysis done. So just a review of the terms. An image is a self-contained snapshot of your applications and all their dependencies. Once the image is built, it doesn't change. A container is just a running instance of your image. I admit that I, along with lots and lots of people, often use these terms interchangeably, and I'm going to try really hard not to do that today because it's technically wrong and you get used to using them interchangeably, and we really shouldn't. An image registry is for storage and delivery of already existing containers. It's basically a website where you can download containers that are already ready to use. Docker is the program that we use to run containers and also pull containers, build containers, etc. A CyVerse tool is a software program that's been integrated into the CyVerse discovery environment, and all the tools in CyVerse discovery environment are Docker containers. And a CyVerse app is just the graphic interface built to go over that particular tool. Again, occasionally we interchange the words tools and app, and I'm going to try not to do that. So just one final point of clarification before we really get started. Images are built from files that specify all the things that need to go into that image, what software you want, and that may be more than one program, obviously, any files that the program needs to have access to in order to run, environmental variables, etc. There are two basic containerization programs that we use here at CyVerse, Docker, and all the containers I'll discuss today are Docker containers. Docker containers, well, Docker images, see, I'm already doing it. Docker images are built from Docker files. And the Docker file is just a text file with a very specific format that tells the program how to build your image, what needs to be in there. Singularity is a different containerization program that's mostly used for running on HPC systems. And Singularity images are built from Singularity recipes. A Singularity recipe serves essentially the same purpose as a Docker file, it's just for a different program. So I say all of this because today I'm going to introduce you to BioConda recipes briefly, and they shouldn't be confused. It turns out recipes is a very generic term and it's been adopted by many groups. And in the case of BioConda, a recipe is the set of files used to build a BioConda package, and those are not actually containers. So just keep that in mind and we'll be good. So to give you some background on the BioConda project, those of you who use Macs will maybe be familiar with the Conda package manager, and BioConda is just a specific channel of the Conda package manager for bioinformatics tools. All of these are hosted in a GitHub repository for the BioConda project, and there's a recipe to build a BioConda package for each and every one of the tools there. Currently, that's more than 6,000 different bioinformatics packages. So the odds are with you that the tool you're looking for is already there. These are, again, just packages for the Conda package manager. But the most important thing for us today is that for each package they add, the BioConda project, because they're awesome, adds a corresponding Docker biocontainer to the key.io image registry, which means that there are more than 6,000 bioinformatics packages that have pre-built biocontainers available for them at key.io. All you have to do is go and get them. So biocontainers specifically is a community-driven project that provides infrastructure and guidelines on bioinformatics containers. Their focus has been predominantly on omics technology, which makes sense. I mean, there are many omics tools available out there, and certainly many more necessary than there were for more reductionist types of biology. I certainly have done a lot more computing than since I got into omics than I ever did as a cell biologist. And they provide containers that are ready to be used by the bioinformatics community. And that's what biocontainers are, and we're gonna try and get some of them today. So, key.io, I may have mentioned, is an image registry. You can sign up and get an account and host your own images there. If you want to build your own containers and make them freely available to the public, you can absolutely do that. An account is not at all necessary to use the biocontainers. They are all publicly available and, most importantly, free. And as I said before, every BioConda package has a biocontainer here. So more than 6,000, and they're adding to that rapidly. I think it was last July, they only had 4,000 packages, or 4,000 biocontainers. And so if your tool's not there, it might be soon, and if not, you can ask for it, and I'll show you how to do that as well. And all the biocontainers are Docker-based. Just keep that in mind. So if we go to key.io, let's see. Okay, that should be big enough for everyone to see, I hope. This is the front page at key.io, and you can see there's a sign-in option here. Again, you can do that if you want, but you don't need an account to get biocontainers from the page. So today I've decided that we will work with the tool called PoreChop, which is a long-read trimming tool for Oxford Nanopore sequencing data. So if you just search for PORCHOP in the search window at the top there, you'll see 3 different things come up. And the bottom 2 are images that another user has made that contain the PORCHOP tool and are also publicly available. But the one we're interested in is the BioContainers image. And so we click on that, and it will take us to the BioContainers PORCHOP repository. There's not a lot of information on this page, but in the bottom right here, you'll see there's a pull command that would theoretically get you this tool. I don't normally use the pull command on the front page here because there's no tag. It doesn't specify what version of the tool you're getting, and I really like to know what I have. And it's really important for your science that, at the very least, if you don't care about the version, you at least know what version you're using. So if you go to the left-hand side of the page, on the Tags tab, you can see that there's a list of different tags that indicate which version of the tool that is. In this particular case, you see that PORCHOP only has the one version, 0.2.3, but there have been many installations, and there are several different images available. I tend to think in these circumstances that the most recently added image is probably the best. So that's this top one here because that's what we've sorted on. At the far right, you can see there's a little arrow icon for fetching tag, and if you click on that, you'll get a drop-down window, and you can select Docker pull by tag. And that provides you with the pull command to get this very image with this particular tag. The tag is what we refer to this part at the end as the part after the colon. So you can click copy command, and we close that. If I go back over here. And then you can paste that command directly onto the command line. So the first line in this particular window is exactly that. I've just pasted it on the command line. You'll see that I used sudo here. That's because the machine I usually run this on, I don't have root permissions for. If you're running this on your laptop, this is probably not going to be a problem for you. So we hit that, and at the bottom here, it'll tell us that it has brought in this new container or new image. See, I'm doing it again. Okay. Now, the next thing you can do is run the container. So again, I need sudo, and this is what it looks like on the command line, but that's actually a little bit difficult to read on a slide. So I've broken it down into manageable chunks for us, and the backslash just represents where I've had a line break entered. Sudo, again, you may not need sudo. Docker run just tells Docker to run the container. --rm removes the container when it's done with your analysis. If you don't do this, eventually they'll start to accumulate and take up space, so it's always a good idea to use the --rm. -v, we're just mounting our current working directory on our local machine into a directory within the container so that we can make our data available for analysis. -w specifies the working directory in the container. And then there's entry point. Entry point is extremely important for biocontainers. If you've seen previous webinars, you may have seen that you can run a container without an entry point, and that in Docker files you can specify an entry point. And all of that's true, except that as a rule, biocontainers don't have built-in entry points. And so you have to specify it on the command line when you run it. Otherwise, you haven't told your container to do anything. Then this is just the name of our image, which in this particular case is extremely long. That tag is a lot longer than the average tag. And then following the image name, you just need to provide the arguments that you would normally provide to whatever tool you're running. In our case, -i is an input file, and -o is an output file. And there are many, many more parameters, but I decided to keep it simple. So while the container is running, it looks a little bit like this. And depending on what your tool is, you'll get various amounts of progress reported back to you. Some tools don't tell you anything, and you just wait and stare until you get your command prompt back. In this case, PORCHOP is fairly verbose, and it gives you a little progress report about looking for how far it is into the process of looking for adapter sets. It shows you which adapter sets it found, and then it trims them. And then at the bottom in the box there, you can see that it's saving that to the output file we specified on the command line. So when your container finishes running, and because we specified RM, it will be removed, your output file should end up in your local directory that you mounted. So if we list our local working directory, you see that the PoorChop output file is now available there and is quite sizable. So at this point in the process, you can run your biocontainer anywhere you can run Docker. So you can run it on your laptop, you can run it on an Atmosphere virtual machine, or on another cloud service. You could run it on an HPC system if you convert your Docker container into a Singularity container, or a Docker image into a Singularity image, I suppose. Keep in mind that you are still limited by the hardware. So if you're running something on your laptop, it needs to be something your laptop can manage. If you're doing long read assembly, you're going to need to do that on an HPC system. If you want to know more about how you can convert your container to a Singularity container, or how you can run your container on a CyVerse Atmosphere machine, then you should look at the webinar from 2 weeks ago by my colleague Tyson Swetno. And he showed you how to do both of those things. So for anyone who's not familiar, I'm just going to give you a little description of the CyVerse discovery environment. It's made to provide graphic interfaces for common analysis tools. All of the tools that are integrated into the CyVerse discovery environment are Docker containers. And you, as a user, we've made it easy in recent times for you to integrate your own tools and then build your own apps as well. So any of these biocontainers can be brought in by you, the user, without any help from us. And once you have a tool and an app, you can keep them private or share them with one collaborator or a whole lab group, or make them public. Anyone with a CyVerse account can use it. So for our next task, we'll do tool integration in the DE of that same PoorChop container. So the first thing you'll need to do is to log into the discovery environment with your CyVerse credentials. Just take me a minute. Okay, so when you get to the discovery environment, it'll look something like this, in case you're not familiar. And you'll need to go to the apps window, which is this button here that says apps. I will maximize that. Once you're in the apps window, in the top right-hand corner, you have the Manage Tools button, which gives you the Manage Tools window. And in the top left corner of the Manage Tools window, you'll find a drop box under Tools that gives you Add Tool. And that's where you get the form to add a tool. This looks like a lot of information, but really only a few of these need to be filled in, and I'll show you which ones those are. I've already filled in a form for the PoorChop tool. And so if I cancel this, back in the Manage Tools window, I can search for PoorChop. And this is the image that we pulled and ran just a minute ago. So because this is mine, you can see that I own it. It's not public. I can still edit this. So if we just select it and then go back to the Tools button in the top left corner and select Edit, it will bring up that same Add Tool form that we saw a minute ago. The tool name is, of course, just PoorChop. There's not any specific syntax you need to use here. I would say keep it simple and as close to the name of the tool as you can possibly get. Description is not specifically required, but it's really nice to have a description, particularly if you're going to make this tool public, because then other users who might want to build a different app using this tool can glance at it and see what it actually does. The version number that we saw before is 0.2.3. In the image name field, you want to enter every part of your image name before the colon. So you can see it ends with PoorChop. And then in tag, you add all the parts of the image name that come after the colon, which we refer to as the tag. Under type, it will be pre-filled as executable, and you should leave it that way. There are other types of apps, but when you're integrating in this particular manner, it's always going to be executable. And here's where things get just a little bit confusing. In the OSG image path, you'll notice I can't even click in there, and that's because this is not an OSG app. OSG is a different option that you can select from the tool drop down. So yeah, can't click in there. It says it's required. It's only required for OSG tools and apps. So just ignore it. But as I mentioned before, entry point is extremely important. And this is, of course, just the command that you use to call whichever tool you happen to be using. And in our case, that's PORCHOP. So when you fill those in, those are all the required information. Leave everything else as it is and click OK. And this says PORCHOP updated successfully. If this were the first time we were filling it in, it would say PORCHOP added successfully. But either way, success is always a good thing. And if we click OK, then that goes away. So now if we wanted to use this tool to build an app, which if you're going to use it in the discovery environment, you're going to have to do because apps are how you do things in the discovery environment. So highlight that, or you could search for it again. And then at the bottom of the tools drop-down menu, there's Use in App. And you can just ignore this error. Okay, you can see because we already specified the PORCHOP tool that it's already pre-filled in this tool used field. And then you'll need to create a name for your app. I would recommend PORCHOP 0.2.3 and an app description. And then from there down, you can begin adding the various fields and files, arguments that you need to run PORCHOP. So I'm just going to close this because I've already created a PORCHOP app based on this tool. And if I close the Manage Tools window, this is back in the Apps window, which we opened in the beginning. Notice that the default is to display apps under development, and these are all of my private apps that haven't been made public. So PORCHOP is right there, and if I highlight that and then go to the Apps drop-down menu, I can still edit it because I haven't made this public. Once you make something public, editing is extremely minimal, and that's just because other people are using it and you don't want to change it too much. That's really not fair. So the app I've already created using the PORCHOP tool, I called it PORCHOP 0.2.3, filled in an app description, and provided all the various inputs that PORCHOP needs, which is quite a few, I might add. So down here at the bottom, you can see it displays what the command line options would look like. And that's what's being supplied to the machine that actually runs it. And so in this case, I don't need to hit save because hopefully I haven't changed anything. And I can just close that. If we go back to the slides. So now you've actually integrated your tool and built an app, you're ready to go. You can do your analysis. So I've just made a summary slide here to show you the basic steps for integrating a biocontainer into the discovery environment. Your first step is just to go to key.io and find a biocontainer image with the tool that you need. And as I said, there's more than 6,000 now, and they're adding to them rapidly. BioConda has done an outstanding job in contributing to the biocontainers and packages. Second step is to just pull your image using a Docker pull command on the command line. Then you need to run your container with appropriate data just to test it and make sure that it works the way you expect it to. And then add your tool in the DE using that Manage Tools button in the Apps window. And then you can build an app on top of your tool to do whatever you need it to do. And then as anything in the discovery environment, you can share your tool or app as much or as little as you wish. I've provided some useful links and references just to help you out. As Tina said, this will appear as a webinar video on YouTube. The slides will also be included in our wiki page, and all of these links are interactive, so you can use this as a cheat sheet to get some of the places you want to go. And I also recommend the BioContainers EDU, which is a documentation for the BioContainers project, and they have a lot of really great basic tutorials and information about biocontainers and what they are and so forth. Also, for all of those things that I did outside of this slide deck in this presentation, I've included print screens that cover that material, so you can refer back to these slides if you'd like at a later date. And with that, I would like to thank, first of all of my colleagues, and particularly Tina, who's put this webinar together, and also a very special thank you to the NSF, as CyVerse is an NSF-supported project. And if there are any questions, I'd be happy to take them.
Thank you, Amanda. I don't see any questions typed into the chat window at this time. You did a great job, step by step, which is, I think, going to be really helpful for people to be able to watch this on their own time and review exactly the steps that you provided. If anybody does have a question, either type it in or feel free to unmute yourself and ask. But while we're waiting, I wanted to tell people that our next webinar, normally scheduled for March 8th, will be canceled due to Container Camp. However, the regular following one on March 22nd will be on deploying scalable interactive bioinformatics analyses via VICE, which is our visual interactive computing environment, an extension of the DE, by special guest Peter Rose of the San Diego Supercomputing Center. This webinar will build on the foundation that Amanda, Julian, and Tyson have provided on containers and demonstrate how Peter's team at the Structural Bioinformatics Lab deployed a prototype app for scalable data mining of the protein data bank. So people might be interested in that. So again, please note that the next scheduled webinar is canceled, but that the following one on March 22nd will be by special guest. Are there any other questions? I'm not seeing any. Oh, wait, let's see. Okay, just a comment from Satish. So with that, thank you everybody very much, and we'll see you hopefully in a month or so online. Bye now.
Bye.